Hi everyone, this is Sina, and today we're gonna talk about affecting variables on knock. So I have created a list here. As you can see, we have different variables affecting knock. We're gonna evaluate them separately, but generally we have RPM, load, ignition angle, variable valve timing set points, intake air temperature, lambda, injection phase for both PFI engines and direct injection engines. We have also geometry compression ratio, carbon deposits, oil, fuel's chemical composition, port, valve, and chamber design, cooling system, and also calibration and engine management system functions. As I said, we're going to cover them separately, each one of them individually. So let's begin with the first one, which is RPM. So imagine you're now operating the engine at 1000 RPM. At 1000 RPM, each engine cycle completes in around 120 milliseconds. The combustion process, if we assume it completes in 60 degrees of crank angle, this equals to 10 milliseconds. But at 5000 RPM, each engine cycle completes in 24 millisecond, or the combustion process itself completes in 2 milliseconds. So, generally speaking, as engine speed goes up, less time is available for a spot in the end gas to reach auto ignition. So, the residence time of the end gas at a given state reduces. So, the probability that it develops into auto ignition and knock decreases with increased RPM. So, in general, the probability of knock happening uh, decreases with rising engine RPM. The second variable being engine load. By engine load, we mean the amount of mass, air mass, especially inside a cylinder. Some people can say, instead of MAF, we can say manifold pressure. But the important thing is MAF is much more accurate regarding load, because at the same imagine this scenario in which you have two different cases with the same amount of manifold pressure sensor reading. So you have equal MAP, but the amount of MAF inside a cylinder, or mass airflow inside the cylinder, can be different depending on the VVD set point or other actuator setups. So MAF is better, uh, but what does load tell us about knock? At higher engine load, we mean higher airflow mass within the cylinder. This translates into higher compression of the end gas as the flame advances, and higher end gas temperature. So during the combustion, as the flame propagates into the end gas, because at higher loads we have higher air and fuel inside the cylinder, and when they combust, they expand behind the flame and they compress the end gas. So at higher loads, this compression is more severe. So you get an end gas with higher temperature. Another effect it has is at higher engine load, we have higher cylinder pressure. It means uh, because the load is up, you have more air and fuel inside the cylinder. You get more pressure even before the combustion takes place. And during the combustion, of course, because you have more energy to be released because of higher amount of fuel, during the combustion also you get higher cylinder pressure. And increased pressure promotes low temperature reaction rates, thus decreasing time to auto ignition. So in general, with increased load, knock probability goes up. Uh, as you can see in this graph here, uh, we have the y-axis shows ignition delay. Ignition delay means the time to auto ignition. Uh, for example, if it's 1 millisecond or here, which is equal to 1 millisecond, it means that at that given state, at that given pressure and temperature, that fuel and air pocket uh, will need 1 millisecond to auto ignite. And the x-axis is 1000 divided by the temperature. So as we go from here to here, temperature goes up. And as you can see, ignition delay decreases with increasing temperature and also with increasing pressure. So higher load causes more cylinder pressure, higher cylinder pressure, and that will result into increased auto ignition and knock probability. So the next variable is ignition angle set point. As you all know, advanced ignition angle results into advanced heat release rate. What does this mean? It means when you advance the ignition angle, you also advance the combustion vent, and the amount of energy released also is advanced. Not the amount, the ignition, the energy release event also advances. And it also happens in lower chamber volume because the piston is moving up or moving down depending on the situation and the ignition angle. But uh, more parts of the energy release is being done during lower chamber volume. So this will result in higher pressure and temperature, which we said both of them promote low temperature reaction rate, decreasing time to auto ignition. So advancing ignition angle also increases knock probability. So as you can see in this graph, we have cylinder pressure and crank angle, and we have three different sets of ignition angles. As you can see, for the most advanced one, we have higher cylinder pressure and also more advanced peak cylinder pressure. This means the combustion is also advanced because of the advanced ignition angle, and as a result, we have higher cylinder pressure and definitely higher cylinder temperature. So advancing ignition angle increases knock probability. So the next variable is VVT set points. VVT have different effects. Most important one being residual content, the amount of residual inside the cylinder, and compressor operating point if the engine is equipped with a turbocharger. And there are also some other effects like changing the effective compression ratio of the engine. But the most important one being residual content, it affects the end gas temperature and it has a dilution effect. So as the residual content goes up, you're going to end up with a higher end gas temperature, which this increases the probability of knock, but at the same time, it also increases dilution. So this has a negative effect on knock probability. It means when you dilute the fuel air mixture, the reaction rates, even the low temperature one, decreases, and because of that, knock probability might decrease. For compressor operating point, you can uh, like if you have a turbocharger and the engine is equipped with that turbocharger with different VVT set points, you're gonna work at different parts of these compressor regions. Like for example, you can work at manifold pressure of 2.2 bars, or for that same amount of torque with different VVT set, you're gonna work around 1.8 manifold pressure. So you're gonna get different intake air temperatures because you have different compression ratios, and also you are working at different parts of the compressor with different efficiencies. So VVT has also effect on intake air temperature. As I said, some other effects like affecting the uh, effective compression ratio. So we cannot say easily what kind of effect at the end VVT has on knock, it depends on uh, different things, like if it increases in gas temperature to a level that promotes knock, but at the same time the dilution effect is negligible, you might get increased knock probability, but if the dilution effect is higher than the higher in gas temperature, you get probably lower knock probability. So for VVT, it's not easy to say what kind of effect it has. It has to be determined differently for each operating point. Intake air temperature, this is pretty obvious. Higher intake air fuel temperature means elevated mixture temperature during the whole engine cycle, including the in-gas at combustion phase, which shortens the time to auto ignition. So when intake air temperature goes up, you're gonna get a higher chance of knock. And because of this, most OEM BMS have correction factors depending on intake air temperature on ignition angle set points. Okay, we get to lambda. Richer fuel air ratios increase flame speed, but not that much. Uh, but they have an effect on flame speed and they increases it. This will reduce the time the in-gas has to reach auto ignition. Just like RPM, as RPM goes up, there is less time available for the in-gas to reach auto ignition. So when lambda goes up, you get, when richer fuel air ratio uh, is introduced inside the cylinder, the flame speed goes up, and you might get lower probability of knock. It also has another effect. Richer fuel air ratios lead to lower mixture temperature because when you increase the amount of fuel compared to a stoichiometric ratio, you get higher evaporation of the fuel, so the mixture cools down more. Uh, but it also has another effect. This one is different. Richer fuel air ratios also elevate the low temperature reaction rate, hence reducing time to auto ignition. Uh, so in the end gas, when the air fuel ratio is richer, its low temperature reactions rate goes up, and this one acts as a ignition delay reducer. But the overall result is reduced knock probability because of this two part, especially this one, lowering the mixture temperature. So in general, decreasing lambda or increasing fuel air ratio, i.e. richer fuel air ratios, results into reduced knock probability. Okay, so what about injection phase? It depends on what type of injection system we have, if it's port fuel injection or direct injection. Uh, so port fuel injection engines with OEM engine management systems have their end of injection before intake valve open. So because of that, a big portion of the fuel evaporates in the intake ports. This is done because it lowers the HC and CO emissions. But if you change this into start of injection after intake valve open, this will result into a lower mixture temperature because a higher portion of the fuel evaporates within the cylinder, cooling the mixture. For direct injection engines, injection occurs within the cylinders, so this will maximize the cooling efficiency. And also for direct injection engines with late injection technology, like injecting during compression, the mixture is less prone to auto ignition because of when you introduce the fuel during the latter time of the compression, that fuel was not present inside the cylinder that whole time, and it was not affected by that cylinder pressure and temperature level, so it has much more time to get to auto ignition. So this will result in a lower knock probability. And because of that, some direct injection engines have some split injection strategy, something like that, which they split the injection into two different intervals during the intake. Some part of that, desired injection mass is introduced inside the cylinder, creating a lean homogeneous mixture. And during the mid parts of the compression stroke, the rest of the fuel is injected in the second injection phase. And with this strategy, they lower the knock probability by a lot. Okay, so now we get to geometric compression ratio. This one is pretty simple. Engine with higher geometric compression ratio are more prone to knock. So this obvious increased compression ratio results into higher pressure and temperature. But at the end, effective compression ratio is the main factor, but higher geometric ratio tends to increase also the effective ratio. So this is very important. Yes, at the end, the effective compression ratio is important. Like VVT has a huge effect on effective compression ratio, but engines with higher geometric compression ratio tends to have higher effective compression ratio as well. Carbon deposits. So, as you all know, all engines after some time they develop carbon deposits inside a chamber, both on the piston crown and the chamber walls. The valves, all parts get carbon deposits. They have three different distinct effects on knock. First one being increasing compression ratio by a little bit. So when you have carbon deposits on these walls, the combustion chamber volume decreases. And because of that, compression ratio goes up by a little bit. The second effect is insulation. When you have these carbon deposits, the heat transfer decreases between the cylinder gas and walls and after that to the coolant. And because of that, you get increased mixture temperature. And because of that, you get more probability of knock. This is the main reason. The third one would be hotspot source. So these carbon deposits, they can heat up and have a lot of temperature, a higher temperature, sorry, and they can act as a hot surface and start auto ignition process in the end gas. So all of these three effects work in harmony to cause more knock. Okay, the next variable is oil. Oil is very important for GDI engines regarding knock. Most GDI engines, when they were being introduced into the market during their first few years, they all had, most of them, they had a common problem called low speed pre-ignition, or LSPI. A lot of research was held to find the root cause of this problem, and it was related to engine oil. So what is LSPI? So you have inside the GDI engines, you have injection inside the cylinder, and some parts of this injection get attached to the and impinge on the cylinder walls, and they mix with the oil film, and they will create an oil fuel film. And when the piston goes up during the compression, because it reaches TDC and it has to stop, it deaccelerates. And because of this deacceleration, Some uh, some of these oil and fuel film, which was formed earlier, fly toward the combustion chamber. Uh, like different droplets are flying inside the cylinder. And these droplets have very low time to auto ignition attribute. Means uh, in that cylinder state, that cylinder pressure and temperature level, they auto ignite so fast, and they will cause pre-ignition. And pre-ignition acts like a very advanced ignition angle and will result into auto ignition and knock in the end gas. Uh, what was the solution? They found out if they add zinc additives instead of previously used calcium additives in engine oil, uh, the time to auto ignition of these droplets increases by a lot and they will not cause pre-ignition. So this was from oil. We get to fuel's chemical composition. So fuel's chemical composition dictates its low and high temperature reaction steps and rates, directly affecting its autoignition characteristics. I'm not going to talk a lot about this one. There's going to be a different video about this one. We will talk about it later. We get to port, valve, and chamber design. So port, valve, and chamber design, they directly affect turbulence level within the cylinder. As you know, turbulence governs the mixing process of fuel, air, and residuals. Higher turbulence increases mixture homogeneity, hence lowering the probability of autoignition turning into detonation. If you remember in the first video, we said mixture heterogeneity creates temperature gradient around inside the end gas region, which after the auto ignition happened at some spot, this can cause uh, the auto ignition turning into detonation or thermal explosion. So increased turbulence increases the mixture homogeneity, hence lowering the probability of auto ignition turning into detonation. Turbulence also increases the flame speed a lot, hence and gas residence time in any given state shortens, thus decreasing the probability of knock. Also, spark plug location and chamber shape affect how far uh, shall the flame travel to consume all of the end gas. If the shape and location, the shape of the chamber and also the spark plug location is not not optimized, this will result into some parts of the end gas has much more time to reach auto ignition, and they might get to auto ignition, so it increases the knock probability. For cooling system, of course, poor cooling system design or functioning results into a higher wall temperature, which elevates the mixture temperature, hence increased knock probability. And at the end, we have calibration and EMS functions. This one is very important. So as you all know, definitely wrong calibrations like wrong ignition angle, basic ignition angles, corrective ignition angles like both factors and additives one, and also wrong knock filtering constants, noise acquisition, and adaptation calibration can definitely result into poor knock detection and also control. So for your engine, the detection part is one thing, controlling it is another thing. Sometimes you have good control strategies, but with very poor detection strategies, so you don't actually detect the knocks, but you can't control them. Uh, and sometimes you have good knock detection strategies, but poor control functions. Both of them are bad. So you gotta have good detection and control strategies, and their calibration also. Another thing is some engine management system with premium knock detection, control, prevention, and adaptation strategies are essential to knock subjects. Yeah, that's it. Definitely, there are some other variables which affect. I didn't mention them because that would be a too long video, and some of them are not that important because they do not happen that much, like poor spark plug choice that can result into knock, but that's kind of not a variable to be considered. So uh, we're not going to talk about those things. So that's it. That's pretty much it, and I hope you liked the video. Please feel free to leave your comments if you have any questions or any suggestions regarding these videos. I would definitely answer them, and I'd love to hear your suggestions. Thank you all. Have a good day. Bye.